In the spring of 1935, in a quiet office at Princeton, the most famous scientist who has ever lived sat down to end quantum mechanics. Albert Einstein was 56 years old, already a living monument, the man whose name had become the word people reach for when they mean genius. He was certain the strange new theory taking over physics was broken at its core. Therefore, he and two younger colleagues wrote 4 pages of cold logic built to expose the flaw and bring the whole thing down, and he expected to win, because he had rewritten reality once already. But the paper did not destroy quantum mechanics. It accidentally uncovered the single strangest thing the theory contains, a phenomenon Einstein would spend the next 20 years calling spooky, refusing to accept, sure to his bones it could not be real. He died in 1955 still sure he was wrong, and the proof of how wrong he was would arrive in pieces he never lived to see, from a lonely theorem written in Belfast, to a basement laser in Berkeley, to light captured from quasars billions of years old, all the way to a Nobel Prize handed out in 2022 for confirming that the thing Einstein hated is as real as the chair you are sitting in. So before we go back to that office in Princeton, get comfortable, and if you have not already, hit subscribe or join so the next one finds you. If you want to go deeper into the wider country this channel wanders through, space, physics, the math, the slow collapse of the things we assumed were solid that lives over on Patreon. Stay with me to the end, because the part that should unsettle you is not that Einstein was wrong about entanglement. It is what the answer quietly says about you, and whether you were ever really one separate thing at all. Let's start where it started. There is a paper sitting in the archives of the journal Physical Review, published on the 15th of May, 1935, that was written for one reason and one reason only: to kill quantum mechanics, to take the most successful physical theory ever devised and prove, with nothing but cold logic, that it was broken at the foundation. The man who organized that attack was the most famous scientist who has ever lived, and he failed so completely, so catastrophically, that the weapon he built to destroy the theory became the single most important discovery the theory ever produced. He found it by accident, while trying to prove it was impossible. The thing Albert Einstein stumbled onto in those 4 pages now runs inside machines that did not exist when he was alive. It is the operating principle behind quantum computing. It is the reason quantum cryptography works. Governments are pouring billions into controlling it right now, this year, while you are listening to this. And Einstein spent the last 2 decades of his life insisting it was not real, that it could not be real, that any universe in which it was real would be a universe too absurd for a serious person to accept. He called it spooky. He did not mean that as a compliment. He meant it as an accusation against a theory he was certain had to be wrong. He was wrong instead, and not in the ordinary way that clever people are sometimes wrong, where they overlooked a term in an equation or trusted a bad measurement. He was wrong about the deepest thing he believed about the nature of reality, the assumption underneath relativity, the assumption underneath everything he ever did. And here is the detail that should sit badly with you, the one I keep coming back to. There is reason to think he suspected it, that somewhere in those last lonely years in Princeton, the man knew the ground was not as solid as he was publicly insisting it was, and he chose to die defending it anyway. You know a particular version of Albert Einstein. Everyone does. The lone genius who saw what the establishment could not. The patent clerk who overturned 3 centuries of physics in a single year. The man whose intuition was so reliable that when the experiments disagreed with him, the smart money bet on the experiments being wrong. That Einstein is mostly real. That is the remarkable thing. He really was right, again and again, against the consensus, when the consensus had every reason to be confident. This is the story of the one time he was the consensus, the one time the lone genius was the entrenched authority defending the old order against an uncomfortable new idea. And the dissent against him was not filed by a rival physicist. It was filed by reality itself, in a series of experiments so precise and so strange that the people who ran them often did not want their own results to be true. The verdict came in slowly, across 60 years, in laboratories in California and France and the Netherlands, using equipment that in one case was triggered by light that left two quasars on opposite sides of the sky billions of years before the Earth existed. The answer that came back, measured to a confidence of 9.3 standard deviations, was that the world is not built the way Einstein needed it to be built. Remember that number, 9.3. We are going to walk all the way to it, and by the time we arrive it is going to mean something you will not be able to set back down. But to understand why a measurement could break a man's life, you first have to understand what that man could not stand about the theory he helped create. Because Einstein was not a crank. He was not a religious objector waving his arms at mathematics he did not understand. He understood the mathematics better than almost anyone alive. He had helped build it. His 1905 paper on the photoelectric effect, the one he actually won the Nobel Prize for, was one of the founding documents of quantum theory. When the New York Times ran the story of the 1935 attack on the 4th of May, the day before formal publication, they described him in the headline as a critic of the theory, and in the body of the article as something closer to family. A sort of grandfather of quantum mechanics, the paper called him. The grandfather had decided the grandchild was a monster. So what was the objection? What did Einstein see when he looked at quantum mechanics that made one of the most generous minds in the history of science turn cold? He saw a theory that was telling him reality does not exist until you look at it. And he could not accept that, not because it offended his sense of comfort, but because he believed it was demonstrably, provably false. And he thought he could prove it in 4 pages. To see the argument the way he saw it, you have to understand 2 commitments that Einstein held so deeply they were almost beneath the level of conscious belief. They were the water he swam in. The first is called realism. Realism is the assumption that things have properties whether or not anyone is measuring them. The moon is there when nobody looks at it. An electron has a position even when no instrument is recording that position. A coin in a sealed box is already heads or already tails before you open the lid. And opening the lid does not decide the outcome. It only reveals an outcome that was already settled. That sounds so obvious, it is hard to even state without feeling foolish. Of course things have properties when you are not looking. What else could they possibly do? The second commitment is called locality. Locality is the assumption that nothing can influence anything else faster than light can travel between them. This one Einstein did not merely believe. He had spent his entire adult life building the theory that made it true. Special relativity, his own creation, established that the speed of light is the absolute ceiling on every causal influence in the universe. You cannot push, pull, signal, nudge, or affect anything at a distance instantaneously. Whatever you do here can only reach there at the speed of light or slower. If realism was the water Einstein swam in, locality was the cage he had personally welded shut around the universe. Nothing gets out. Nothing moves faster than light. The structure of space and time forbids it. Put those 2 commitments together, and you get a worldview so reasonable that it feels less like a theory and more like sanity itself. The world is made of separate things. Each thing has its own definite properties. Those properties are real and settled whether or not you observe them. And the only way one thing can affect another is by sending some influence across the space between them, at the speed of light or slower. Einstein had a name for this combined picture, or at least history has assigned him one. Local realism. It is the belief that the universe is a collection of independent objects sitting in their own locations, carrying their own private, pre-existing facts. And quantum mechanics, the theory he had helped to found, was quietly telling him that not one part of that picture was safe. Now there is a phrase you have heard attached to all of this, and I want to deal with it now because it gets the chronology exactly backwards in almost every telling. The phrase is, God does not play dice. People treat it as Einstein's verdict on entanglement, on spooky action, on the whole non-local mess. It was not. He wrote it in a letter to his friend Max Born on the 4th of December, 1926, almost a decade before the paper we are discussing. And the thing he was objecting to in that letter was not action at a distance at all. It was randomness. The version most people half remember is a paraphrase. What he actually wrote was that the theory said a great deal, but did not really bring us closer to the secret of the old one, and that he, at any rate, was convinced that he does not throw dice. The complaint was about quantum mechanics making the universe fundamentally probabilistic, deciding outcomes by chance rather than by law. The worry about distant things secretly touching each other came later, and it came specifically out of the work we are about to examine. So when you hear God does not play dice presented as the headline of Einstein's war with entanglement, you are hearing two different objections, raised 11 years apart, melted into one slogan. The dice were 1926. The spookiness was still years away. He had not even found it yet. He found it in Princeton, in the company of two men who were both young enough to be students of the legend they were working beside. By the autumn of 1933, Einstein had left Germany for good. He was 54 years old, a refugee from a country that had begun burning his books and putting a price on his head, and he had landed at the brand new Institute for Advanced Study, a research haven attached in spirit, if not in administration, to Princeton University. He had no teaching duties. He had no real obligations at all except to think. What he wanted to think about was the incompleteness of quantum mechanics, and for that, he needed collaborators willing to chase an argument that most of the physics world considered already settled and lost. The first was Boris Podolsky, born in the town of Taganrog in southern Russia on the 29th of June, 1896. Podolsky was 38 in the year of the paper, a capable mathematical physicist with a restless career that had already taken him through California and the Soviet Union and back. He was the one who could turn a verbal argument into formal machinery, and he was the one Einstein trusted to write the thing up. The second was Nathan Rosen, a Brooklyn kid, born on the 22nd of March, 1909, which made him 25 when the work began and barely 26 when it was published. Rosen was Einstein's assistant. He was, by the standard of the room, a child. And the three of them, the grandfather and the mathematician and the kid, sat down to build the trap. Here is the argument they built, and I am going to walk you through it slowly, because the entire rest of this story is the universe's response to it, and you cannot feel the response if you do not first feel the force of the original blow. The paper has a famously dry title. Can quantum mechanical description of physical reality be considered complete? It is the kind of title that hides a knife. They began by defining what they meant by an element of reality, because the whole argument turns on this definition and they wanted it to be unimpeachable. Their criterion was careful and modest. If, without disturbing a system in any way, you can predict with certainty. meaning with probability equal to 1, the value of some physical quantity, then there exists an element of physical reality corresponding to that quantity. Read that again, because it is doing a lot of quiet work. They are not making a wild metaphysical claim. They are saying something almost impossible to argue with. If you can know for certain what a measurement will give before you make it, and without touching the thing you are measuring, then the property you are predicting must already be real. It must already be there. How else could you predict it with perfect certainty without going anywhere near it? The certainty has to be coming from somewhere, and the only honest place for it to come from is the thing itself, already possessing the value, waiting to be found. That is realism. Stated as a criterion you would have to be unreasonable to reject. And then they sprang it. Imagine two particles that interact briefly and then fly apart, off in opposite directions, until they are as far from each other as you like. A meter, a kilometer, a light year. The distance is going to matter enormously later, so hold on to it. According to quantum mechanics, because the two particles interacted, their descriptions are now linked. The mathematics binds them together into a single combined state, even as they separate across any gulf of space you can imagine. And that linkage has a consequence that Einstein, Podolsky, and Rosen proceeded to squeeze until it screamed. Suppose you measure the position of the first particle. Because the two are linked, the laws of quantum mechanics let you predict, with perfect certainty, the position of the second particle instantly without ever going near it. By their own criterion, that means the second particle's position is an element of reality. It is really there, a definite fact, settled, fine. But now suppose that instead you had chosen to measure the first particle's momentum, how fast it is going and in what direction. The same linkage now lets you predict the second particle's momentum with perfect certainty, again without touching it. So by the very same criterion, the second particle's momentum is also an element of reality, also really there, also settled. And there is the trap closing. Because you did not go anywhere near the second particle, you only measured the first one, far away. Whatever you did over here could not, by Einstein's own sacred principle of locality, have reached over there and created a fact about the distant particle. The speed of light forbids it. So the second particle must have had both a definite position and a definite momentum all along, sitting there, real, waiting, regardless of which measurement you happen to choose to make on its partner. But quantum mechanics flatly forbids that. The theory's most famous result, the Heisenberg uncertainty principle, says a particle cannot simultaneously possess a definite position and a definite momentum. The more precisely one is defined, the more hopelessly undefined the other becomes. The theory does not say we cannot measure both at once. It says they cannot both be real at once. So here is the box Einstein, Podolsky, and Rosen believed they had built with no way out. Either the second particle really does have a definite position and momentum at the same time, in which case quantum mechanics is incomplete, because it cannot describe properties that are demonstrably real. Or measuring the first particle somehow reaches across the entire distance, instantly, and conjures the second particle's properties into existence from nothing, in which case locality is violated and the foundation of relativity cracks. They considered the second option for exactly as long as it took to dismiss it. No reasonable definition of reality, they wrote, could be expected to permit this. They could not imagine a sane universe in which a measurement here decides a fact there, faster than light, with no signal passing between. So they took the only door they thought was left. Quantum mechanics, they concluded, is incomplete. There must be a deeper theory underneath it, one that restores definite properties to everything and keeps every influence local and slower than light. And the paper ends, almost gently, with a statement of faith. They believed such a theory was possible. That was the weapon, logically clean, almost impossible to attack on its own terms, and aimed directly at the heart of the theory. And the most remarkable thing about it, the thing almost nobody tells you, is that even as it was being published, Einstein was already unhappy with it. Because the paper had a flaw he could see and could not fix. Not a flaw in the logic, a flaw in the framing. And it would take the world 30 years to discover that the real flaw was somewhere else entirely. Somewhere none of the three men had thought to look. The flaw Einstein could see was this. He had not written the paper. Podolsky had, and Podolsky, being the mathematician of the group, had buried the argument under a mountain of formalism, layers of symbolic machinery that made the thing look like a technical result about wave functions, rather than what Einstein understood it to be, which was a simple and devastating statement about the structure of reality. Einstein wanted to say something a child could grasp. The world is made of separate things, and separate things have their own separate properties, and you cannot change one by poking the other from across the room. Podolsky had taken that and dressed it in equations until the body underneath was hard to find. We know exactly how Einstein felt about this because he complained about it in writing a few weeks after publication. To the one man on earth who he thought might actually understand the stakes. On the 19th of June, 1935, he wrote to Erwin Schrodinger that the paper had been written by Podolsky after a lot of discussion, but that it had not come out as well as he had originally wanted. The essential thing, he said, had been smothered by the formalism. That word, smothered, is the tell. He felt that the heart of his argument had been suffocated under Podolsky's mathematics, and he was right that something had gone wrong, even if he had the wrong idea about what. And it got worse, because Podolsky did something Einstein found close to unforgivable. He talked to the press. Before the paper was even out, the New York Times had the story, which is why the famous headline calling Einstein an attacker of quantum theory appeared on the 4th of May, 11 days before the paper itself reached the world. Einstein detested that kind of pre-publication publicity, the leaking of unfinished science to newspapers, and he issued a stiff public statement distancing himself from the whole circus. The collaboration between the three men effectively ended there. Podolsky drifted out of Einstein's orbit and into a long, strange career that would much later include, according to declassified Soviet intelligence files published decades after his death, a quiet stint passing information to the Soviet Union about wartime physics. The mathematician who helped Einstein argue that reality must have definite, hidden properties spent part of his own life as a hidden property the United States government did not know it possessed. I am not going to pretend that connects to the physics in any deep way. It just sits there in the record, too strange to leave out. But strip away the formalism and the press leak and the wounded feelings, and look at what Einstein actually believed he had shown, in his own preferred language. He came back to it many times over the following years, always trying to state it more cleanly than Podolsky had. And in his hands, it stopped being about position and momentum at all. It became about something he called separability. The idea is almost unbearably reasonable. If two systems are far apart in space, then they are genuinely two systems. Each has its own independent reality. Whatever is true of the one over here is true regardless of what you do to the one over there, because they are separate, and separation is supposed to mean exactly that the two have come apart into distinct existences that no longer reach into each other. Einstein said, in so many words, that without this assumption of the independent existence of spatially distant things, physics as he understood it would not be possible at all. It was not one belief among many. It was the precondition for doing science the way he knew how to do it. You need to feel how total that commitment was, because it explains everything that follows, including the stubbornness that would eventually look like tragedy. Einstein was not defending a pet theory. He was defending the possibility of a knowable world. If you cannot assume that distant things have separate, independent realities, then in his view you cannot really speak about any one thing at all, because everything is potentially contaminated by every other thing, everywhere, all at once. That is not a universe. That is a smear. And he would rather believe that the most successful theory in physics was secretly incomplete, riddled with missing pieces waiting to be discovered, than accept that the universe was a smear. So he placed his bet. Quantum mechanics is incomplete. There are hidden variables, deeper facts the theory does not yet capture, and when we find them, separability will be restored, locality will be safe, and the dice will turn out to have been loaded all along by laws we simply had not learned to read. It was a reasonable bet. It may be the most reasonable bet anyone has ever lost. The first person to write back was the one person who understood it well enough to make it worse. Erwin Schrodinger was at this point an exile like Einstein, an Austrian physicist who had fled the Nazi regime, brilliant, restless, romantically and personally, chaotic in ways that scandalized the staid academic world he moved through, and the author of the wave equation that sat at the very center of the quantum mechanics they were all arguing about. He had built a load-bearing wall of the house Einstein was now trying to condemn. And when the EPRA paper landed, Schrodinger did not rush to defend his own creation. He did something far more interesting. He agreed that Einstein had found something genuinely disturbing, and then he went deeper into it than Einstein had been willing to go. In a letter, and then in a pair of papers published through the Cambridge Philosophical Society, later that same year of 1935, Schrodinger gave the phenomenon a name. In the original German, he called it Verschränkung, a word that carries the sense of folding together, of crossing and interlocking, like arms crossed over a chest or the slats of a folded lattice. When he wrote about it in English, he translated it himself, and the word he chose is the word we still use: entanglement. When two systems interact and then separate, he wrote, they can no longer be described independently of each other, the way they could before they met. By the interaction they have become entangled. Their fates are folded together and will not come apart simply because the particles have flown to opposite ends of the laboratory or the opposite ends of the galaxy. And then Schrodinger wrote a sentence that should be far more famous than it is, a sentence that quietly reverses the entire emotional thrust of Einstein's attack. He said that entanglement was not one interesting feature of quantum mechanics among others. He called it the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Sit with what he was saying. Einstein had presented entanglement as the absurd consequence that proved the theory broken. Schrodinger looked at the very same thing and said no. This is not the bug. This is the engine. This strange folding together of distant systems is not the embarrassing flaw in quantum mechanics. It is the single feature that makes quantum mechanics different from every theory that came before it. The thing Einstein was holding up as a reason to reject the theory was, in Schrödinger's eyes, the most important thing the theory had ever revealed. Two of the greatest minds of the century looked at the identical phenomenon. One saw proof that reality could not work this way. The other saw the deepest truth physics had ever touched, and the experiments had not been done yet. There was no way in 1935 to decide between them. It was, for the moment, a war of intuitions and both men had the best intuitions in the world. Schrodinger was so unsettled by where the logic led that in the same burst of work, he produced the most famous thought experiment in the history of science, and he produced it as an expression of disgust, not delight. The cat. You know the cat. A cat sealed in a box with a vial of poison rigged to a single radioactive atom, so that if the atom decays, the poison releases and the cat dies, and if it does not, the cat lives. Quantum mechanics says the atom, until measured, is in a combination of decayed and not decayed, both at once. And Schrödinger's point, the point everyone forgets, was not that this is wondrous. It was that this is ridiculous. If the atom is in a smear of both states, and the cat's life is chained to the atom, then the theory is telling you the cat is in a smear of alive and dead, and that is plainly preposterous, and the fact that the theory leads there is supposed to bother you. The cat was a weapon too. It was Schrödinger and Einstein, allies in skepticism, both trying to drag the absurdity of the quantum world up to a scale where ordinary human intuition could see it and recoil. Einstein loved the cat. He wrote to Schrödinger that it showed the situation most elegantly. The two old exiles, cornered by a theory they could not defeat, taking grim satisfaction in at least having made its strangeness impossible to ignore. I want to be honest about something here, because this framework I am working inside rewards certainty, and the honest thing is to resist it at exactly this point. In 1935, Einstein and Schrödinger were not being foolish. They were not clinging to superstition against evidence. There was no evidence. Their intuition, that the world is made of separate things with their own properties, is the intuition that every functioning human being uses every second of every day, and it had never once failed in the entire history of physics up to that moment. They were defending common sense with the full force of two of the finest minds ever to consider the problem. If you had been in the room, you would have been on their side. I would have been on their side. That is what makes what comes next so hard to absorb. It was not the foolish who were wrong. It was the wise. But intuition is not a measurement, and a war of intuitions has to be settled by someone willing to fire back. And the man who fired back was not Schrödinger, who agreed with Einstein, but the one figure in this story who had spent more than a decade as Einstein's designated opponent, his philosophical rival, the keeper of the orthodoxy that Einstein was trying to burn down. When the EPA paper reached him, it did not find a calm man ready with an answer. It found a man who, by the account of those around him, came close to panic. Niels Bohr was the most powerful man in physics. Not the most famous, that was Einstein, but the most powerful in the way that matters inside a discipline. His institute in Copenhagen was the gravitational center of quantum theory, the interpretation that had become orthodoxy. The one taught in every classroom, carried the name of his city. When a young physicist wanted to know what quantum mechanics meant, the answer they received had been shaped, filtered, and approved by Bohr. He was the high priest of the idea that Einstein had just attacked. And the attack was aimed precisely at the soft spot in his doctrine, the question of what is real before you measure it. We have an eyewitness account of what happened when the paper arrived, because Bohr's assistant at the time, Leon Rosenfeld, wrote it down. Rosenfeld said the EPA paper came down upon them as a bolt from the blue. The moment Bohr heard the argument, everything else was abandoned. Whatever Bohr had been working on, it stopped. Rosenfeld described his boss trying to dictate a response and getting tangled, starting over, falling into long silences, and at one point muttering the names of the authors in a kind of mocking sing-song, Podolsky, 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 as if by ridiculing the man who wrote the paper, he could diminish the argument inside it. This is not the behavior of a man who has an answer ready. This is the behavior of a man who has been hit somewhere he did not expect to be hit, by an opponent he respected. And who knows that the entire edifice he has spent 15 years defending is now being watched to see whether it holds. It took him more than 6 weeks. 6 weeks for the most authoritative interpreter of quantum mechanics alive to formulate a reply to a 4-page paper. And when the reply finally appeared in Physical Review on the 15th of October, 1935, he had done something almost insolent. He had given his rebuttal the exact same title as the EPRA paper, word for word. Can quantum mechanical description of physical reality be considered complete? The same question, posed as if Einstein had never asked it. And then, underneath that title, he had written a reply so dense, so convoluted, so resistant to plain understanding, that physicists have been arguing about what it actually says for almost 90 years. Here is roughly what it says, as best as anyone can reconstruct it. Bohr attacked the one phrase in the EPRA criterion that the 3 authors had thought was unassailable, the phrase without in any way disturbing a system. Einstein, Podolsky, and Rosen had assumed that measuring the first particle does not disturb the second one, because they are far apart, and locality forbids any disturbance crossing the gap. Bohr agreed that there was no mechanical disturbance. He agreed nothing pushed or pulled on the distant particle. But, he argued, there is still an influence. Not a force, not a signal, but an influence on the very conditions that define what can meaningfully be said about the distant system. By choosing what to measure here, you define what it is even possible to predict there. And that definitional act reaches across the gap in a way that is not a violation of relativity, but is also not nothing. The properties of the distant particle, in Bohr's view, were never sitting there waiting to be revealed. They do not exist as definite facts until the whole experimental arrangement, including the choice of what to measure, is specified. There is no separate little particle over there carrying its own private position and momentum. There is only the entire situation, indivisible. If that explanation left you slightly seasick, you are in excellent company. It left almost everyone seasick, including, eventually, Bohr himself. Decades later, rereading his own reply, he admitted in print that there was an inefficiency of expression in those passages that must have made it very difficult to appreciate the line of the argument. That is a Nobel laureate, the architect of the orthodox interpretation, looking back at the single most important thing he ever wrote about the foundations of his own field and conceding that he could barely follow it. One historian has described Bohr's reply as obscure in content but confident in tone, and that combination is worth holding on to, because it is the exact texture of authority defending itself when it does not actually have the answer. Confident in tone, obscure in content. You have heard that voice. You have probably been on the receiving end of it. And here is the part you were never told, the part that should genuinely change how you think about this whole episode. Bohr did not win that argument. Not really. What happened was that the physics community decided he had won, which is a completely different thing. The two are not the same, and the gap between them is where this entire story lives. By consensus, by the sheer institutional weight of Copenhagen, by the fact that quantum mechanics kept producing correct predictions, and the philosophical question of what it meant seemed like a luxury nobody could afford. The field simply agreed that Bohr had handled Einstein and moved on. Generations of physicists were taught that the old man had raised an interesting objection and that Bohr had answered it, and that the matter was closed. Some of the sharpest historians and philosophers of physics who have gone back and actually read the exchange line by line have concluded something close to the opposite. that Bohr's reply was philosophically a retreat, a withdrawal into a kind of positivism that refused to engage with the real question rather than answering it. The verdict of history was not delivered by the evidence. It was delivered by exhaustion and authority. And it would stand, unchallenged in any way that mattered, for nearly 30 years. This is the moment to name something directly, because it recurs through the rest of the story, and you should see it coming each time. The orthodox position that hardened after 1935 was not really a theory about what is happening in nature. It was an instruction to stop asking. Do not ask what the particle is doing between measurements. Do not ask whether it has a position before you look. Do not ask what is real when no one is watching. These questions were declared not wrong, but meaningless, unscientific, the mark of someone who had failed to absorb the lesson of the quantum revolution. The Copenhagen interpretation, in its hardest form, is not an answer to Einstein's question. It is a refusal to permit the question. And a refusal to permit a question, dressed in the robes of scientific maturity, is one of the most effective ways ever devised to bury something that might otherwise have to be confronted. The phrase that captures the era that followed is one that physicists themselves use, sometimes with pride and sometimes with embarrassment. Shut up and calculate. The idea was that quantum mechanics worked. Its predictions were confirmed to absurd precision. You could build lasers and transistors and understand the chemistry of the entire periodic table with it. So who cares what it means? Stop philosophizing, stop asking childish questions about reality and separateness and what the cat is doing in the box, and get back to computing the numbers that experiments could check. To even express curiosity about the foundations was to mark yourself as soft, unserious, the kind of person who would never get tenure. The questions Einstein had raised did not get answered. They got socially exiled. A young physicist in 1950 who admitted to losing sleep over the Eppler paradox was a young physicist quietly advised to change topics if they wanted a career. I find this genuinely enraging, and I think you should too, because it was not a conspiracy, and that is exactly what makes it worse. Nobody sent a memo. Nobody banned the questions. It was just understood, in the way that the most powerful prohibitions are always just understood, that some doors were not to be opened by anyone who wanted to be taken seriously. The deepest question in the theory, the question of whether the world is made of separate real things, was placed in a drawer, and the drawer was not locked by force. It was locked by embarrassment. For 40 years, the most important unresolved problem in physics was treated as a slightly disreputable hobby, and the man who finally walked over and opened the drawer did it, by his own description, as a hobby, on the side, in whatever hours he could steal from his real job. He was not a famous foundations rebel. He was a working particle physicist at a European laboratory, and he picked the lock not because he wanted to defend Einstein, although secretly he did, but because he had read the exchange and concluded that the entire physics establishment had been kidding itself for a generation. He thought Einstein had been treated unfairly. He thought Bohr had won by intimidation rather than argument, and he set out, in his spare time, to do the one thing nobody had managed in 30 years, to turn the war of intuitions into something a machine could decide. His name was John Stuart Bell, and he was about to do something that neither Einstein nor Bohr had imagined was possible. He was going to find the experiment hidden inside the philosophy. John Bell was born in Belfast on the 28th of July, 1928, into a working-class Protestant family that did not have the money to keep a clever boy in school past the age where most children went to work. His family scraped together what they could, and Bell, who had decided he wanted to be a scientist before he fully understood what one was, made it to Queen's University Belfast, where he took first-class degrees in experimental and then mathematical physics. He went on to a doctorate under Rudolf Peierls at Birmingham, finished in the mid-1950s, and then spent his career as a working physicist. First at the British Atomic Energy Research Site at Harwell, and then, from 1960 onward, at CERN, the great particle physics laboratory straddling the border between Switzerland and France. His job was accelerator design and particle theory. Real, fundable, respectable physics. He moved to Geneva with his wife Mary, who was also a physicist, and who would be his collaborator and sounding board for the rest of his life. The Quantum Foundation's work, the work that would eventually be called the most profound discovery of science, was not his job. He called it his hobby. He pursued it in stolen hours, partly because he knew perfectly well that admitting too loudly to caring about the meaning of quantum mechanics was a way to not be taken seriously, and the social prohibition I described a moment ago applied to him as much as anyone. So the man who would crack open the most important question in the field did it quietly, on the side, the way another physicist might restore an old motorcycle. And you need to understand whose side he was on, because it is the engine of the irony that drives everything from here. Bell loved Einstein's argument. He thought it was correct in spirit, that Einstein had seen clearly what Bohr had only obscured. Years later, he told the writer Jeremy Bernstein, in an interview that has become one of the most quoted passages in all of Quantum Foundations, that he felt Einstein's intellectual superiority over Bohr in this matter was enormous. A vast gulf, he said, between the man who saw clearly what was needed and the obscurantist. He used that word for Bohr, obscurantist, one who deliberately obscures. And then he said the line that should be carved over the entrance to this entire subject. So for me, he said, it is a pity that Einstein's idea does not work. The reasonable thing just does not work. Hold that sentence, because we are walking toward the moment it comes true, and it was Bell himself who proved it, against his own hopes. He set out to vindicate Einstein. He wanted local hidden variables to be possible. He wanted there to be a deeper layer of definite, pre-existing properties underneath quantum mechanics, restoring the sane world of separate things. And in the course of trying to map out how such a theory would have to behave, he discovered that it could not behave the way the world actually does. He found the wall by walking into it. Here is what he found, and I am going to build it up the way he did, starting from the most reasonable possible picture, the one Einstein wanted. Because the only way to feel the force of Bell's result is to first believe, sincerely, that the reasonable picture has to be true. People reach for an analogy at this point, and it is worth using because it is exactly the analogy that Bell's theorem destroys, which makes it the most instructive wrong answer in physics. Imagine I take a pair of gloves, separate them into two identical boxes, and mail one box to you in Tokyo and one box to a friend in Toronto. Neither of you knows which glove you have. You open your box in Tokyo and find the left glove. In that instant you know, with perfect certainty, that your friend in Toronto has the right glove. Did anything travel between Tokyo and Toronto when you opened your box? Of course not. Did opening your box reach across the world and force your friend's glove to become right-handed? Of course not. The gloves were already left and right when they were sealed in the boxes back home. Your knowledge changed instantly. The world did not. There was nothing spooky about it at all. There was just a fact you did not have access to until you looked. That is the local hidden variable picture, and it is precisely what Einstein believed was happening with his two particles. They were not in a mysterious smear of both states. They were like the gloves. They left the interaction already carrying definite properties, hidden from us, and measuring one simply reveals the matching fact about the other. No faster than light influence required, no spookiness, just hidden information being uncovered. It is so satisfying. It dissolves the entire paradox. And it is wrong. And Bell figured out how to prove it is wrong. And the way he did it is one of the genuinely beautiful things the human mind has ever produced. The trick was to stop measuring the particles in just one way and start measuring them along different, randomly chosen settings, like rotating the dial on each detector to different angles, independently on each side. If the particles really are like gloves, carrying a full set of pre-existing answers for every possible angle you might choose, then the statistics of how often the two sides agree and disagree as you vary the angles are mathematically constrained. There is a limit to how correlated the results can be. Bell wrote that limit down. It takes the form of an inequality, a ceiling, a number that the agreement between two distant detectors can never exceed if the world is made of local, pre-existing, glove-like facts. Any universe built the way Einstein wanted, with definite hidden properties and no faster than light influence, has to obey that ceiling. It is not a feature of any particular theory. It is a feature of the entire category of theories Einstein was betting on. That is the staggering thing about what Bell did. He did not test one rival idea. He found a single number that every possible local realistic theory, including ones nobody has even thought of yet, is forbidden from crossing. And then he calculated what quantum mechanics predicts for the same measurements. And quantum mechanics sails straight past the ceiling. The theory predicts correlations between the two distant detectors that are stronger than any glove-like locally real world could ever produce. The two pictures do not just disagree philosophically anymore. They disagree numerically. They make different predictions about what a real detector will actually count. For 30 years, the difference between Einstein and Bohr had been a matter of taste, of intuition, of which absurdity you found easier to swallow. Bell turned it into a horse race with a finish line. Run the experiment, count the coincidences, compare the number to the ceiling. If the world stays under the ceiling, Einstein was right. The particles were gloves all along. And quantum mechanics is incomplete. If the world breaks through the ceiling, Einstein was wrong. The gloves picture is dead, and reality does something that no locally real universe is permitted to do. His paper, titled On the Einstein-Podolsky-Rosen Paradox, appeared in 1964 in a brand new and frankly obscure journal called Physics, which paid its authors instead of charging them, and which folded after only a few years. The single most important paper on the foundations of quantum mechanics in the second half of the 20th century was published in a journal that almost no one read and that did not survive. It sank, at first, almost without a trace. Bell had built the instrument that could decide the deepest question in physics, and for several years, essentially nobody noticed. I want to pause on the cruelty of the irony, because the framework I am writing inside tells me to find the moment where the personal and the physical are the same thread, and here it is, naked. Bell was Einstein's man. He thought Einstein was right. He wanted to hand the old man a posthumous victory, because by 1964 Einstein was 9 years dead and could not defend himself. And what Bell actually did, the thing his name will forever be attached to, was build the only machine capable of proving Einstein wrong. He sharpened the knife, hoping it would never have to be used, hoping that when someone finally ran the experiment, the world would stay obediently under the ceiling and Einstein would be vindicated. The reasonable thing just does not work. He said that line knowing it applied to his own dearest hope. He spent the rest of his life finding the experimental results, when they came, puzzling rather than satisfying. He never stopped wishing the gloves were real. Bell had a sense of humor about it, the dark, precise humor of a man who has made peace with an unwelcome truth without ever quite liking it. He had a colleague at CERN named Reinhold Bertelsmann, a physicist famous in the building for always wearing socks of 2 different colors, never matching, every single day. And Bell wrote a paper, one of the most charming things in the literature, called Bertelsmann's Socks and the Nature of Reality. His point was this: when you see one of Bertelsmann's feet sticking out from behind a door and it is wearing a pink sock, you know instantly that the other foot, wherever it is not wearing pink. No mystery. The colors were chosen that morning. They are pre-existing facts. The socks are gloves. And Bell's argument was that quantum particles are not like Bertelsmann's socks. The correlations between them are too strong, too tightly coordinated across distance, to be explained by colors chosen in advance. Something stranger is happening, something the socks cannot account for, and Bell had proven it had to be stranger, with an inequality that the socks could never violate, but that nature apparently could. So now there was a wall, and on one side of the wall stood every reasonable assumption a human being has ever made about the world being composed of separate things with their own properties, and on the other side stood the bare predictions of quantum mechanics, and Bell had shown that an experiment could tell you which side reality actually lived on. And this is where you should start to feel the shape of the thing approaching. The second time I am going to point at it before we arrive. Because notice what is at stake in the inequality. Bell's result does not merely threaten locality, the no faster than light rule. It threatens something underneath it. To stay under the ceiling, a theory needs 2 ingredients. It needs locality, and it needs the gloves to be real, the properties to exist before they are measured. That second ingredient has a name: realism. And the terrible elegance of Bell's theorem is that if the world breaks the ceiling, you do not get to keep both. At least one of them has to die. Either nothing has definite properties until it is measured, which kills realism, or distant things instantly reach into each other, which kills locality. Maybe both, but not neither. The experiment, if it broke the ceiling, would not just prove Einstein wrong about one thing. It would force a choice between 2 beliefs so basic that most people do not even know they hold them, and there would be no version of the answer that lets you walk away with your intuitions intact. All that was needed now was for someone to actually build the apparatus, cool the equipment, choose the angles, and count. And the first person to do it would discover, the way Bell had, that he had built a machine to destroy the very thing he was hoping to save. The man was John Clauser, and in 1972, he was a young physicist at the University of California at Berkeley, who had read Bell's forgotten paper and become quietly obsessed with it. Almost nobody thought the experiment was worth doing. The prevailing attitude was that quantum mechanics was obviously correct, that running inexpensive, finicky experiment to confirm it yet again was a waste of a career, and that anyone who took the foundation's questions seriously was wasting their time on philosophy. One senior physicist reportedly told Clauser that doing the experiment would be a mistake that could damage his prospects. Clauser did it anyway, and he did it for a reason that should sound familiar by now. Like Bell, like the men who started all of this, he was rooting for Einstein. He has said it plainly in an oral history interview recorded decades later. The result, he said, was not the one he expected. He had hoped they would overthrow quantum mechanics. He wanted the world to stay under the ceiling. He wanted the gloves to be real. He built the apparatus with a graduate student named Stuart Friedman, who was born in 1944 and who would do much of the painstaking experimental labor in a basement laboratory in Burge Hall on the Berkeley campus. The heart of it was a small glass cell of calcium atoms, heated until they glowed. When you excite a calcium atom in just the right way, it relaxes by emitting 2 photons of light, one after the other, in a rapid cascade. And those 2 photons come out entangled in their polarization, the orientation of their light waves folded together in exactly the way Schrodinger had described. Clauser and Friedman sent the 2 photons in opposite directions to 2 polarization detectors, set at various angles, and counted how often the 2 sides agreed. The detectors were modest, the photon source was dim, and to gather enough events to get a statistically meaningful answer, they had to run the experiment for something on the order of 200 hours of accumulated counting. 200 hours of sitting in a basement, watching coincidences tick up one at a time, to settle a question that Einstein and Bohr had fought over with nothing but words. The work built on a refinement of Bell's inequality, worked out a few years earlier, in 1969, by Clauser together with Michael Horn, Abner Shimoni, and Richard Holt, a version practical enough to actually test in a real laboratory with imperfect equipment. So when the counting was done, they had a clean number to compare against the ceiling. And the world did not stay under the ceiling. The correlations Clauser and Friedman measured broke through Bell's limit and landed right where quantum mechanics said they would, in violation of any locally real account, by a margin of about 6.5 standard deviations. In the language of experimental physics, that is not a hint or a suggestion. That is a result you can stand on. The gloves were not real. Einstein's reasonable world had failed its first real test, and the man who ran the test had been hoping with his whole heart for the opposite outcome. He got the number, checked it, and accepted that the universe had told him no. That should have been an earthquake, a confirmed experimental result, settling a question Einstein himself had posed, showing that the world is not locally real. It should have been front-page news. It was, instead, met largely with a shrug. Of course quantum mechanics is right, the establishment said. We told you that. Why did you bother? The very people who had refused for decades to take the question seriously now treated its experimental resolution as a foregone conclusion that had never needed testing. First, the question was meaningless. Then, the moment it was answered, the answer was obvious. The one thing the result was never allowed to be was important. I keep coming back to that pattern because it is everywhere in this story, and because it is, I think, the real scandal underneath the physics. Not that the truth was hidden by villains, but that it was waved through by a culture so certain of itself that it could not register what it was looking at. But there was a crack in the result, and the determined defenders of local realism, the few who were left, knew exactly where it was. Because an experiment is never as clean as a theorem, and every gap between the ideal experiment and the real one is a place where Einstein's world might still be hiding. These gaps have a name. They are called loopholes, and the next 40 years of this story is essentially a war fought over closing them, one by one, while the holdouts retreated into each remaining gap in turn. The first and most important loophole is the locality loophole, and it is the one that matters most because locality was the whole point. In the Clauser and Friedman setup, the 2 detectors were only a few meters apart, and crucially, the angles of the detectors were set in advance and left fixed during the run. Here is the problem. If the detectors are close together and their settings are decided ahead of time, then in principle there is enough time for some influence, traveling at or below the speed of light, to pass from one detector to the other, or from the source to both, carrying information about how the measurement is set up. And if that is possible, then the particles, or the source, could in principle conspire, using perfectly ordinary slower-than-light signals to fake the quantum correlations. It sounds paranoid. It is paranoid. But the entire question is whether the world is local, and you cannot close that question while leaving open the possibility that local signals did all the work. The skeptic could still say, with a straight face, that the particles cheated using a hidden message sent at light speed or below, and that no faster than light spookiness was involved at all. To slam that door, you would need to change the detector settings so fast, at the last possible instant, that no signal traveling at light speed could carry the news from one side to the other in time to matter. You would need to decide how to measure each particle only after the particles were already in flight and too far apart to coordinate. The man who did it was a French physicist named Alain Aspect, working at the Institut d'Optique in Orsay, just south of Paris, with his collaborators Jean Dalibard and Gérard Roger. Across a series of increasingly refined experiments in the early 1980s, Aspect pushed the test far past anything Clauser had managed. His two-channel experiment in 1982 measured a violation of Bell's inequality with a value of 2.697, where any locally real world is forbidden from exceeding 2, and where quantum mechanics had predicted a value of about 2.7. The agreement with quantum mechanics and the violation of Einstein's ceiling was the strongest anyone had ever recorded to that point, and the uncertainty was tiny, around 15 thousandths. The world was not just over the ceiling, it was sitting exactly where Bohr's theory said it would sit, to a precision that left no room to argue. But the experiment that made Aspect's name, the one that eventually carried him to Stockholm, was the one that closed the locality loophole. He built an apparatus in which the orientation of each detector was switched back and forth extremely rapidly by acousto-optical devices, switches driven by sound waves in a medium, flipping the measurement setting roughly every 10 billionths of a second. The two stations were about 12 meters apart. At the speed of light, it takes light around 40 billionths of a second to cross 12 meters. So by switching the settings every 10 nanoseconds, far faster than light could carry any message across the gap, Aspect ensured that at the moment each particle was measured, there was no way for one detector to know how the other was set, and no way for the source to have known in advance either. The choice of measurement was being made while the particles were already in flight, too late for any slower than light conspiracy to coordinate the outcome. He had, in effect, asked the universe the question and slammed the door before it could phone a friend. The landmark paper, Experimental Test of Bell's Inequalities Using Time-Varying Analyzers, appeared in Physical Review Letters on the 20th of December, 1982. The inequality was violated by 5 standard deviations, with the settings changing too fast for light to carry the secret. The locality loophole was, for the first time, genuinely closed in a real experiment. If the particles were cheating with hidden local signals, those signals would have had to travel faster than light to do it, which is precisely the spooky thing the whole local realist program existed to avoid. The escape hatch had been welded shut. To still believe in Einstein's world after Aspect, you had to retreat to the remaining loopholes, the smaller and stranger ones. And the people who did retreat there were, increasingly, not defending a physical picture so much as defending the possibility that a physical picture might somehow still exist. I find Aspect's results more unsettling than Clauser's, and not because of the better numbers. It is the timing detail that does it. Sit with what the time-varying analyzers actually mean. The decision about how to measure the particle on the left was being made after the particles had already separated, and the particle on the right responded as if it knew, even though the decision had not been made yet when the particles parted ways, and could not have reached it in time afterward without breaking the speed of light. There is no story you can tell about that using gloves. There is no set of pre-written answers the particles could have carried, that would account for correlations responding to choices made after the particles were already too far apart to communicate. Something about the way the two distant events lined up was not being arranged by anything passing between them at all. And we still had not reached the bottom, because the remaining loopholes, the ones the holdouts fled into next, would take another 3 decades and some of the most exquisite experiments ever performed to close. The closer the door got to fully shut, the stranger the thing trapped inside the room turned out to be. There were 2 loopholes left, and they were subtler than the first, which is exactly why the holdouts could live inside them for so long. The first is the detection loophole, sometimes called the fairness loophole, and it goes like this. In every one of these early experiments, the detectors missed a great many of the photons. They were inefficient. They caught only a fraction of the particles that were actually produced, and the experimenters had to assume that the ones they happened to catch were a fair, representative sample of all of them. But what if they were not? What if, by some perverse arrangement of the hidden variables, the particles that get detected are a biased subset, cherry-picked by nature in a way that fakes a violation of Bell's inequality, even though the full ensemble, if you could see all of it, would stay obediently under the ceiling? It is a desperate hope. But it is logically open, and so long as your detectors are inefficient, the skeptic gets to keep it. The second is the freedom of choice loophole, and this one is genuinely strange enough that it bends back toward the metaphysical. Bell's whole argument assumes that the experimenter is free to choose the detector settings independently of whatever the particles are doing. But what if that freedom is an illusion? What if the choice of how to set the detector and the hidden properties of the particles were both secretly determined in advance by some common cause reaching back into their shared past, so that the settings and the particles were correlated from the start, conspiring without any of the participants knowing it? If the universe rigged the choice and the particles together at some point in their common history, then the apparent violation could be a kind of cosmic stage trick, and no real spooky action would be needed. This is the loophole that shades into what physicists call superdeterminism, and we will come back to it, because it is the one door that, strictly speaking, can never be fully closed, and because the reason it cannot be closed tells you something uncomfortable about the limits of the entire enterprise. The campaign to close these loopholes ran across the 1990s and 2000s and turned into one of the great experimental sagas of modern physics. In 1998, Anton Zeilinger and his group, then in Innsbruck, ran a version with the 2 detector stations separated by about 400 meters, with the measurement settings chosen by independent quantum random number generators at each station at the last instant, closing the locality and freedom of choice loopholes far more rigorously than Aspect had been able to. And they reported a violation by more than 30 standard deviations. 30. The number had grown from Clauser's 6.5 to a figure that, in any other branch of science, would be considered not a result, but a verdict. And still each experiment closed only some of the loopholes at once, never all of them simultaneously. And the holdouts could always point out, correctly, that no single experiment had yet sealed every door in the same run. As long as that was true, a determined believer in local realism could stitch together the surviving gaps from different experiments and maintain that the reasonable world had not yet been definitively ruled out. It was an increasingly tortured position, but it was not yet impossible. It became impossible in 2015. That was the year 3 separate groups, within months of each other, performed what are called loophole-free Bell tests, experiments that closed the locality loophole and the detection loophole at the same time, in the same run, leaving no gap for a local realistic explanation to hide in. The first and in some ways the most elegant, came from a team led by Ronald Hansen at Delft University of Technology in the Netherlands, published in the journal Nature in late 2015. And the cleverness of their design is worth describing, because it solved the detection problem in a way nobody had managed before. Instead of fragile photons that detectors routinely miss, they used the spins of single electrons trapped inside nitrogen vacancy centers, tiny defects in diamond crystals, defects where a nitrogen atom sits beside a gap in the lattice and traps an electron whose spin can be read out with near-perfect efficiency. They placed 2 of these diamonds in 2 separate laboratories on the Delft campus, 1.3 kilometers apart, and through an intricate procedure called entanglement swapping, they entangled the 2 distant electron spins, then measured them with settings chosen fast enough and detectors efficient enough to close both loopholes at once. The distance mattered. 1.3 kilometers gives light a little over 4 millionths of a second to cross the gap, and the measurements and setting choices were completed faster than that, so no light speed signal could have coordinated the 2 sides. And because the electron spins could be read out with essentially perfect efficiency, there was no inefficient detector to hide a biased sample behind. Both doors shut in the same experiment for the first time in the 80-year history of the argument. The result was a violation of Bell's inequality with a value of 2.42 against a ceiling of 2, with a statistical significance corresponding to a probability of about 3.9% that a locally real world could have produced the data by chance. That p-value was later driven far lower as more data came in. Within the same months, 2 photonic experiments, one led by Marissa Justina in Vienna and one led by Lyndon Shalm at the American Standards Laboratory in Boulder, Colorado, closed the loopholes by a different route using detectors of unprecedented efficiency and reported violations with overwhelming significance. 3 groups, 3 different physical systems. The same answer. The world is not locally real, and now there was no loophole left standing in which to hope otherwise. Except one, the freedom of choice loophole, the strange one, the one that asks whether the experimenters were ever really free to choose their settings at all. Closing that one fully is impossible in principle, because you can always imagine the correlation reaching back further. But you can push it back. You can make the moment at which the settings were chosen earlier and earlier, further and further into the past, so that any common cause linking the choices to the particles would have to reach back across a more and more absurd stretch of history. And in 2018, Zeilinger's group did something that I still find difficult to describe without my voice doing something strange. They used the universe itself as the random number generator. The experiment is called the Cosmic Bell Test, and it was published in Physical Review Letters in August of 2018. To choose the detector settings, the team did not use a quantum random number generator in the lab. They pointed telescopes at 2 quasars, 2 extraordinarily distant and ancient objects on opposite sides of the sky, and they used the color of the light arriving from those quasars, photon by photon, to decide how to set each detector. One quasar's light had been traveling toward Earth for around 7.8 billion years. The other for an even longer stretch. That light left those objects before the sun and the Earth existed, before there was a laboratory or a physicist or a human eye to receive it. And the team used it, the instant it arrived, to set the measurement angles. The point is devastating in its simplicity. For the freedom of choice loophole to save local realism now, the conspiracy linking the detector settings to the hidden properties of the particles would have to have been arranged at least 7.8 billion years ago, encoded into light streaming from opposite ends of the observable universe. waiting all that time to rig a quantum optics experiment in Austria. The result was a violation of Bell's inequality by 9.3 standard deviations, with a probability of a local realistic explanation, by chance, of less than about 7 in 10 to the 21st. The authors wrote that their experiment pushed any local realist mechanism back to at least 7.8 billion years ago, and excluded such mechanisms from about 96% of the entire space-time volume of the past of the experiment, stretching from near the Big Bang to today. There is the number I asked you to remember, 9.3. And now you know what it cost to get it, and what it rules out, and how far back into the history of the universe the holdouts had to retreat in order to find a place to stand. They had been chased out of the laboratory, out of the present, out of the solar system, all the way back to within a sliver of the beginning of time, and even there, in 96% of all the history there has ever been, the door was shut behind them. In 2022, on the 4th of October, the Nobel Prize in Physics was awarded to Alain, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Read the citation carefully. It does not say they discovered something quantum mechanics predicted. It says they established the violation of Bell inequalities. They proved that the world breaks the ceiling. They proved, by experiment, that the universe is not locally real. 87 years after Einstein, Podolsky, and Rosen sat down to demonstrate with cold logic that such a universe was too absurd to take seriously. The Swedish Academy handed out its highest honor to the men who demonstrated, with cold equipment, that we live in exactly that universe. At the Nobel banquet, Aspect did something that ties the whole human thread together. He said that the recognition should go first to the late John Stuart Bell, without whom none of them would have been there. Bell, who had built the instrument hoping it would vindicate Einstein. Bell, who never received the prize because he had died suddenly of a cerebral hemorrhage in Geneva on the 1st of October, 1990, at the age of 62, and the Nobel is not awarded to the dead. And here is the detail that I cannot stop thinking about, the one the framework would call a delayed reveal, except that reality delivered it without any help from a writer. In the year of his death, 1990, John Bell had reportedly been nominated for the Nobel Prize. He may have been weeks, or at most a year or two, from the recognition he had earned. He died before it could reach him. The man who turned the deepest question in physics from philosophy into measurement was in the end exactly like the man he had hoped to vindicate. He did the work that changed everything, and then he died on the wrong side of the recognition, before the world caught up to what he had done. That is two of them now. Einstein, who posed the question, dead before it was answered. Bell, who made it answerable, dead before the answer was honored. There is a pattern in this story, and it has nothing to do with the quality of the physics. The people who saw furthest kept dying in the gap between the seeing and the proving. And here is a thing that should make you angry in a different way than the suppression did, because it is the inverse of suppression, and it is happening right now. While those men were dying unrecognized, the thing they had proven was quietly being turned into machinery, and nobody told you about that either. You were not told the question existed. Then you were not told it had been answered. And now you are not being told that the answer is being welded into the infrastructure of the next century while you sleep. On the 16th of August, 2016, China launched a satellite from the Jiuquan Center on the edge of the Gobi Desert and named it Mikius, after an ancient Chinese philosopher. Its purpose was entanglement. In 2017, a team led by the physicist Jian Wei Pan used Misius to do something that would have ended Einstein's argument in a single afternoon if he had been alive to watch it. The satellite generated pairs of entangled photons in orbit and beamed one photon of each pair down to a ground station at Zeilinger and the other to a station near Lijiang, two observatories in China separated by 1,203 kilometers. The photons fell through the entire depth of the atmosphere, through cloud and turbulence, and hundreds of kilometers of air to opposite ends of a distance that dwarfs every laboratory test ever run. And the entanglement survived. The two photons, now more than 1,000 kilometers apart on the surface of the Earth, still violated Bell's inequality. The spooky action held, from orbit in the open sky, across a gap you could see on a map. Read that slowly, because it is the opening claim of this whole story coming back to collect. I told you at the start that governments are pouring billions into controlling this. Here is what that looks like in practice. By 2020, the same group had used satellite distributed entanglement to perform secure communication between ground stations 1,120 kilometers apart. The reason a nation will spend a fortune on this is that a key shared through entanglement cannot be secretly intercepted, because the very act of measuring the photons to steal the key disturbs them in a way that announces the theft. The non-locality Einstein called a fairy tale is now the basis of communication that cannot, even in principle, be wiretapped. The thing he reached for the most contemptuous word in his vocabulary to dismiss is, at this moment, being engineered into the backbone of what people are calling the quantum internet, into national security systems, into the set of technologies that powerful states now consider too strategically important to be allowed to fall behind on. Spooky action at a distance has a budget line. It has a satellite in orbit. It has a place in the arms race between great powers. And it is not only communication. The entire field that the Nobel Committee specifically named in its citation, quantum information science, rests on entanglement as its raw material. The quantum computers that companies and governments are racing to build, burning through sums that would have funded the whole of Einstein-era physics many times over, do what they do precisely by entangling their components, by forcing many particles into exactly the kind of shared, non-separable state that Einstein insisted could not coherently exist. Every serious quantum computing program on the planet is, at its foundation, an effort to manufacture and control at scale the precise phenomenon that Einstein, Podolsky, and Rosen presented as proof that the theory had to be broken. They thought they had found the absurdity that would bring quantum mechanics down. Engineers are now trying to mass-produce that absurdity because it has turned out to be the most valuable computational resource ever discovered. The argument meant to be a knockout blow became a product roadmap. There is no more complete way to lose a fight than to have your finishing move turned into the other side's flagship technology, and then to not be alive to watch it ship. So the real situation is this. The phenomenon that the greatest physicist who ever lived spent his final 20 years insisting could not be real, that he was certain marked quantum mechanics as broken and incomplete, has now been confirmed from space, honored with the highest prize in science, and built into hardware being deployed by the most powerful nations on Earth. And the average educated person has heard of essentially none of it. They have heard of relativity. They can recite that energy equals mass times the speed of light squared. They carry a vague image of Einstein as the gentle patron saint of physics, who was always, eventually right. They have almost never been told that his last great campaign was a defeat, that he lost it not to a rival, but to reality itself, and that the instrument of that defeat is passing over their heads in low orbit. This is not an accident of public attention. It is the same machine that buried the question in the first place, running in reverse. First, the question was too embarrassing to ask. Then the answer was too obvious to celebrate. Now the technology is too quiet to notice. At every single stage across 90 years, the most important thing in the room was the thing almost nobody was talking about. I keep returning to one phrase, and I cannot make it stop being true. To not be alive to see it. De Broglie silenced, then revived only after he had given up the fight. Bohm exiled, his theory ignored until it had stopped being his. Everett driven out of physics entirely, the worth of his idea admitted only after he was gone. Bell dead a year, perhaps two, short of the prize that had his name written all over it. Einstein dead 9 years before the argument could even begin to be settled, and 67 years before it was crowned in Stockholm. The pattern has nothing to do with the quality of the physics, because the physics was right every time. The pattern is about timing. It is about the merciless gap between the moment a person can see a truth and the moment the world is willing to admit it, and about how reliably that gap turns out to be just long enough to swallow a human life. The truth itself is patient. It has, as the quasar experiment showed, been content to wait since within a sliver of the beginning of time. People are not patient. People die in the gap. That is the tragedy threaded through every part of this, and it is larger than any one man, even though one man is its clearest case. And the question they left behind, the one all of this was supposed to settle, was settled in only the narrowest sense. We now know, beyond any reasonable doubt, that the world is not locally real. What we still cannot agree on, what no experiment has ever been able to touch, is what that actually means. Because proving that Einstein's world is impossible does not tell you which world we live in instead. It only tells you that one of the things you are sure of has to be surrendered. And the moment you ask, which one? The agreement that held all the way through the experiments dissolves into a war that is still being fought right now, with no end in sight. Before we walk into that war, I have to take one escape route away from you, because it is the route almost everyone reaches for the moment they understand what entanglement does. And it is wrong. And the way it is wrong matters. When you hear that measuring a particle here instantly fixes the correlated outcome of its partner there, across a kilometer or across the galaxy, the natural thought is that you could use this to send a message faster than light. Flip a particle in your lab and have its twin twitch in mine, and we have a telephone that beats the speed of light, and relativity is broken after all. It is the first thing nearly everyone imagines, and it does not work. You cannot send a signal this way, not one bit. The reason is subtle, and it is the hinge on which the whole strange truce between quantum mechanics and relativity turns. When you measure your particle, the outcome you personally get is random. You do not control it. You cannot choose to make your particle come out a particular way in order to encode a message. And when your distant partner measures their particle, what they see on its own looks like pure random noise, with no pattern in it whatsoever. The correlation, the spooky coordination, only appears later, when the two of you bring your two lists of results together and compare them side by side. And bringing the lists together requires sending them through some ordinary channel, an email, a phone call, a courier, all of which crawl along at the speed of light or slower. So relativity survives. You cannot use entanglement to talk faster than light, to send information, to break causality. The universe is non-local in what it correlates, but it is scrupulously, almost suspiciously careful to never let that non-locality carry a usable message. It will rig the dance of two distant particles to a precision no local world could match, and it will not let you send so much as a single yes or no across the gap by doing it. That combination, non-local correlation that nonetheless forbids signaling, is one of the strangest facts in physics, and almost nobody outside the field has ever been told it, even though it has been understood for decades. So whatever is happening, it is not a faster-than-light telephone. It is something for which we genuinely do not have a good word, because every word we have was built for a world made of separate things, and the thing we are trying to describe is the failure of separateness itself. Now, the war. Bell proved that to explain the experimental violations, you must give up locality, or give up realism, or give up both. Every serious interpretation of quantum mechanics is, at bottom, a different decision about which of those to sacrifice, and each one buys its survival at a price most people would find unbearable if they understood it clearly. The orthodox Copenhagen view, the one that hardened around Bohr, makes its peace by abandoning realism. It says the particles simply do not have definite properties before measurement. There are no hidden gloves. The position, the momentum, the polarization, none of it is real, and waiting until the act of measurement brings a definite value into being. Before you measure, there is only the wave function, a mathematical object encoding probabilities, and the question of what the particle is really doing in the meantime is declared improper. The kind of question a grown-up physicist learns not to ask. This is the view most working physicists were trained in, and notice that it is not so much an explanation as a discipline, a set of things you agree not to wonder about. It keeps locality, at the price of telling you that the solid definite world you think you live in does not have definite properties when you are not interrogating it. The moon, in the strongest version, is not there in any definite sense when nobody looks. The many worlds view, first proposed by a young physicist named Hugh Everett in 1957, makes a different and in some ways even wilder trade. It keeps locality and it keeps determinism, and it does it by abandoning the assumption that a measurement has a single outcome. In this picture, when you measure the particle, every possible result actually happens, each in its own branch of a constantly splitting universe. The reason your distant partner's results correlate with yours is that the splitting itself propagates outward at the speed of light, with no faster than light influence required, because nothing was ever decided that needed to be communicated. There is no spooky action, because there is no single fact for the action to coordinate. Everett's idea was ridiculed in its time, and he left academic physics entirely, going to work for the defense establishment, embittered, and the human cost in his family was severe in ways I will not exploit for effect here. The interpretation that may have solved the measurement problem was driven to the margins for decades because its author could not survive the institutional cold, and only revived long after he had given up. That pattern again. It keeps relativity intact at the price of telling you that there are uncountable versions of you branching every instant, and that the singular continuous self you experience is a kind of local illusion riding one twig of an endlessly forking tree. It is worth slowing down on how Everett's idea was treated, because it is the same machinery of burial running again, just with different hands on the controls. Everett wrote the work as a doctoral thesis at Princeton under John Wheeler, who happened to be one of Bohr's most devoted admirers. The original manuscript was long and unguarded, and it said, in effect, that the orthodox account of measurement was incoherent and that his own picture, with no collapse and no special role for the observer, was cleaner. Wheeler, caught between his brilliant student and his reverence for Bohr, pressed Everett to cut it down and soften it, to strip out the language that read as an attack, and the version that finally reached print in 1957 was a fraction of the original, muted to the point where many readers could not tell what was being claimed. Even gutted, it was ignored. Then, in the spring of 1959, Everett traveled to Copenhagen, hoping to make his case to Bohr in person, to win over the one man whose blessing would have changed everything. The meeting was a failure of the most quiet and complete kind. Bohr and his circle were not persuaded and were barely engaged, and Everett came away understanding that the door was not going to open. He did not write another physics paper. He went to work for the defense establishment, on weapons targeting and operations research, the mathematics of how many would die in a nuclear exchange, and he made money. And he largely stopped speaking about the idea that should have made his name. For roughly a decade, the interpretations sat in the literature like an unmarked grave. It was another physicist, Bryce DeWitt, who pulled it back into view at the end of the 1960s, who gave it the phrase many worlds that finally made people pay attention, and who assembled the anthology that turned a forgotten thesis into a live position. By the time the field was ready to take Everett seriously, Everett had been gone from physics for years and was not interested in coming back. He was right enough that the idea is now taught and defended at the highest levels, and he was treated badly enough that he never wanted to hear about it again. That pattern, once more. Then there is the pilot wave theory, and this one I cannot tell you about without anger, because it is the cleanest example in the whole story of the pattern I keep naming. The idea goes back to Louis de Broglie in the 1920s and was rebuilt in full mathematical detail by David Bohm in 1952. It keeps realism. The particles always have definite positions, real, the way Einstein wanted. It keeps determinism, and it pays for this by being explicitly, unapologetically non-local, with a guiding wave that connects the particles across any distance and steers them in a way that depends instantly on the configuration of the whole system. It reproduces every prediction of standard quantum mechanics exactly. It is not fringe, it is not crackpot. It is a fully worked out, mathematically consistent theory that gives the right answers. And it was not so much refuted as buried. De Broglie had abandoned the idea under withering criticism in the 1920s and was effectively silenced. When Bohm revived it in 1952, the reception was brutal. One of the founders of quantum theory dismissed work in this vein in language that amounted to calling it juvenile. Bohm himself, hounded out of the United States during the anti-communist hysteria of the McCarthy era, his passport eventually confiscated, spent years in exile in Brazil, isolated from the community that should have engaged with his work. De Broglie silenced, Bohm exiled. The theory shelved, not because it was wrong, because it was not wrong, but because it was non-local and inconvenient, and arrived at the wrong political moment carried by a man the establishment found easy to discard. Bell himself, by the way, was inspired by Bohm. It was reading Bohm's supposedly impossible theory, a theory the textbooks had declared could not exist. That set Bell on the path to his theorem. The buried idea seeded the discovery that vindicated the question Einstein had asked. Nothing in this story stays buried cleanly. It just waits. And then there is superdeterminism, the freedom of choice loophole grown into a full worldview, which keeps both locality and realism by denying that the experimenters were ever free to choose their settings. If the entire history of the universe, including every choice every physicist has ever made about how to orient a detector, was fixed from the initial conditions in a way correlated with the hidden properties of every particle, then the violations can be explained with no spooky action and no loss of definite properties. The price is the surrender of the idea that you can do science at all, that you can independently sample the world, that your choices are not secretly conspiring with the things you are measuring. Most physicists reject it, not because it has been disproven, because it cannot be disproven. That is precisely the problem. But because a theory that explains everything by denying your freedom to test anything, has paid for its consistency with its own scientific usefulness. It is, in the language one might borrow from the founders of this argument, not so much a theory as a surrender. There are others. The view called cubism says the wave function is not out in the world at all, but is a measure of an agent's own beliefs, so that the collapse at measurement is just the updating of one observer's expectations, and the spookiness dissolves because there was never an objective shared state to coordinate. Each interpretation is a different room, and each room has a price of admission posted on the door, and the prices are, respectively, the loss of a definite world, the loss of a single self, the loss of locality, the loss of free choice, the loss of an observer-independent reality. You may pick whichever loss you can best live with. What you may not do, what nature has forbidden by experiment, is keep all of them. The bill is real, and it must be paid in one currency or another. And here is the move that I think is the actual heart of all this, the thing the entire 87-year argument was secretly building toward, and it is the part that the survey of interpretations is designed to set up. After you have laid out all these rooms, all these wildly different stories about what is going on underneath, you notice something that should stop you cold. They disagree about almost everything. They disagree about whether the wave function is real or just bookkeeping. They disagree about whether the universe splits. They disagree about whether particles have positions. They disagree about whether the future is open. On nearly every question that matters, the interpretations are at war. But there is exactly one thing they all agree on, and they agree on it because the experiments leave no choice. Every single one of them has abandoned local realism. Every one. The Copenhagen view gave up the real definite world. Many worlds gave up the single outcome. Pilot wave gave up locality outright. Superdeterminism gave up your freedom. Cubism gave up the observer-independent state. Not one survivor kept the thing Einstein could not let go of, the picture of a world made of separate things, each carrying its own definite properties, none of them reaching faster than light into the others. That picture is dead in every room in the building. The interpretations are not arguing about whether Einstein's world is gone. They are only arguing about what to replace it with. The one belief that every faction has been forced to bury is the exact belief Einstein said was the precondition for physics itself. Sit with that, because it is the thing nobody quite says out loud at the dinner table version of this story. The disagreement among physicists about quantum mechanics is often presented as evidence that the whole thing is still up for grabs, that nothing is really settled, that you can believe whatever you like. The opposite is true. The disagreement is fierce precisely because the one thing that is settled is so unbearable that people will pay almost any other price to avoid facing it directly. They will accept infinite branching universes. They will accept that reality is only their own belief. They will accept that they were never free. They will accept faster than light guidance waves. They will accept anything at all, rather than the bare fact underneath all of it, which is that the world is not made of separate things sitting apart from one another with their own private pre-existing properties. That is not one interpretation among many. That is the floor of the building, and every room is built on it, and the reason there are so many rooms is that nobody wants to live on the floor. And you are about to find out that this was never really a story about particles in a laboratory in Austria. Because if the world is not made of separate things, then the question that has been waiting at the bottom of this the entire time, the question I have been walking you toward since the first minute, is what that makes you. You who feel so completely, obviously separate. You who are sitting there, bounded by your own skin, a single thing in a single place, looking out at a world of other separate things. That feeling of being a discrete object in a definite location, with your own private properties, is the human scale version of exactly the picture that nature has now ruled impossible at its foundation. And the experiments do not stop politely at the edge of the laboratory. They are statements about the basic fabric that you are also made of. But before we follow that all the way down, I owe you the end of the human story, because the man who started all of this did not get to see a single one of the experiments, and the shape of his last years is the cruelest part of the whole account. By the late 1940s and into the 1950s, Einstein at the Institute for Advanced Study was a kind of living monument that the rest of physics had quietly walked past. He was revered and ignored at the same time, which is a particular and lonely fate. The young physicists building the future of quantum field theory treated him with enormous respect and almost no engagement. He knew it. He once described himself, with the dry accuracy he kept to the end, as a man who was generally regarded as a sort of petrified object, rendered blind and deaf by the years. He knew that his colleagues considered him a heretic, out of touch, a great man who had taken a wrong turn somewhere around 1925 and never found his way back to the main road. He spent those years chasing a unified field theory, a single framework that would tie gravity and electromagnetism together, and, he hoped, restore the deterministic, local, classical kind of reality that quantum mechanics had taken from him. He never found it. The unified theory failed. He was working on the equations almost literally to the end, and they never came together, and some part of him surely knew they were not going to. Think about the ironic exactness of it. Einstein had built his entire objection on separability, on the independent existence of spatially distant things, on the world being made of separate parts that do not reach into one another. And he spent his last 2 decades as separate as a human being can be made, walled off inside his own legend, his ideas no longer reaching into the work of the people around him. A man whose isolation had become as complete and as principled as the metaphysics he was defending. He asked the universe to be a collection of independent things keeping to themselves, and he was given a life that looked exactly like that, and it was the loneliest thing imaginable. The personal and the physical were not separate threads in his case either. He had demanded a separable world, and he was made to live in one. On the 17th of April, 1955, an aneurysm in his abdominal aorta, a weakening in the wall of the great artery that had been diagnosed years earlier, began to give way. He was taken to the hospital in Princeton. Surgery might have bought him some time, and the doctors wanted to operate, and he refused. What he said when he refused has been recorded by those who were there, and it is the most Einstein thing he ever said. He told them it was tasteless to prolong life artificially. He said he had done his share, that it was time to go, and that he would do it elegantly. He died in the early hours of the 18th of April, 1955, at the age of 76. Beside his bed were pages covered in the equations of the unified field theory he never completed, the last work of a man still trying. At the very end, to build the local, real, separable universe he was certain had to be there underneath. In the final moments he said something, a few words, but he said them in German, and the night nurse who was with him did not speak German. And so the last words of the most famous mind of the 20th century were lost in the gap between 2 languages. Spoken to someone who could not understand them, there is no recovering them, they are simply gone. A man who spent his life insisting that reality has definite properties, whether or not anyone is there to register them, died saying something real and definite that no one was equipped to receive. He died in 1955. Now hold the timeline against that date, because this is the wound at the center of everything. Bell did not publish his theorem until 1960, 49 years after Einstein was in the ground. The argument that finally made Einstein's question answerable did not exist while Einstein was alive. Clauser and Friedman did not run the first experiment until 1972, 17 years too late for him to hear the result. Aspect did not close the locality loophole until 1982. The loophole-free tests did not come until 2015. The quasar light did not set the detectors until 2018. The Nobel was not awarded until 2022, 67 years after his death. Every single thing that bears on whether Einstein was right or wrong about the deepest question he ever asked happened in a world he was no longer in. He posed the question, and then he left, and the answer arrived to an empty chair, and it kept arriving, decade after decade, to the same empty chair, each new experiment a letter delivered to a man who could no longer read it. He went to his grave, believing he would be vindicated. He believed the hidden variables would be found, that separability would be restored, that the dice were loaded by laws we had not yet learned to read. He died on the losing side of an argument that had not yet been decided, certain he was on the winning one, and he never knew. That is the thing I cannot get past. He never knew. He was spared the verdict by dying before it came, which sounds like a mercy and is actually the opposite, because it means he spent his last lonely years certain of a thing that the universe was waiting to refute the moment he was gone. And I told you at the very beginning that there is reason to think he suspected it, and I have to be honest with you about how thin that reason is, because the framework I am working inside would happily let me overstate it, and the truth is more uncertain and more interesting than a clean claim would be. There is no letter in which Einstein confesses that he thinks he is wrong. He never wavered in public, and there is no clear evidence he wavered in private. But he understood his own argument better than anyone, and his argument, the real one underneath Podolsky's formalism, had always been a fork. Either quantum mechanics is incomplete or the world is non-local. He bet his life on the first branch, but he was far too rigorous a thinker not to see that the second branch was sitting right there, fully formed, the entire time. He had stared directly at the possibility that the world is non-local, and he had called it spooky and turned away from it, not because he had disproven it, but because he could not bear it. A lesser mind would not have seen the second branch at all. Einstein saw it clearly and chose the other one, and spent 20 years defending the choice. Whether that is the same as suspecting he was wrong, I cannot tell you. But he knew the door was there. He had drawn the map himself. He just refused, to the end, to walk through it. Now let me take you down the last step, the one this was always going toward, because the experiments are not a story about laboratories. Entanglement is not a delicate, exotic thing that only appears when a physicist coaxes 2 photons out of a calcium atom in a basement in Berkeley. That is how we study it, in clean isolated pairs, because that is the only way to measure it precisely. But entanglement is the generic condition of matter, not the exception. Anytime 2 systems interact, they entangle. Their descriptions fold together and do not fully come apart afterward. The reason the world does not look like a seething web of non-local connections is not that entanglement is rare. It is that it is everywhere, spread so thickly and shared among so many particles at once that for any 2 specific things the shared correlation gets diluted into the background and becomes nearly impossible to detect. The isolation of a clean entangled pair is the artificial state. The natural state of the universe is everything tangled into everything else through the long history of every interaction that has ever happened. Every particle in your body has interacted with other particles, which interacted with others, in a chain reaching back through the food you ate and the air you breathe, and the star that forged the atoms you are made of. And entanglement does not politely erase itself when the particles part. The separateness you feel, the clean boundary between you and the world, is not the fundamental situation. It is the diluted, averaged out, large-scale appearance of a reality whose actual fabric is woven the other way. And here is where it gets worse, because there are two ways the world could have failed to be locally real. And almost everyone who hears this story fixates on the wrong one. The dramatic one, the one that gets the attention, is the failure of locality, the spooky action, the idea that distant things reach into each other faster than light. It is vivid, and it is frightening, and it is the part Einstein named. But look again at what the interpretations actually surrendered. Most of them did not give up locality at all. They gave up the other thing. They gave up realism. And realism is the quieter assumption, the one you do not even notice you are making, which is exactly why its loss is the harder one to absorb. Realism is the belief that things have definite properties before you look, that the value is there, sitting in the particle, waiting. Bell's theorem and the experiments that followed it mean that for a vast range of the most natural ways of thinking, you cannot keep that. The property is not there beforehand. There is no fact of the matter about the particle's position, or its polarization, or its spin along some axis, until the measurement happens, not hidden from you, not unknown to you, not there. The definite value does not exist as a definite value until reality is forced by the act of measurement to commit to one. That is the part Einstein could not survive, and it is the part you should not be able to set down easily either, because the entire intuition of being a person in a world depends on it. You believe, without ever having decided to believe it, that the world has definite properties when you are not looking, that the room behind you is still there, fully detailed, every object in its place, while your back is turned, that the chair has a definite position, whether or not anyone observes it. This is the assumption Einstein elevated into a principle and called the precondition of physics. And it is the assumption that the experiments have made impossible to hold in its simple form. The world, at its foundation, does not appear to carry the definite, pre-existing, observer-independent properties that your entire sense of being a solid thing in a solid place is built on. Something gets decided at measurement that was not decided before, and the deepest interpretations cannot agree on what does the deciding, or whether anything does, only that the comfortable picture of values quietly sitting in things, waiting to be read, is gone. You are not exempt from this. That is the thing the laboratory framing is designed to let you avoid, and I am not going to let you avoid it. Because following it to where it actually goes is the only honest thing to do with it. You are not standing outside the quantum world looking in at it through the window of an experiment. You are made of the same fabric as the particles in the calcium cell. The atoms in your hand obey the same rules that broke Bell's inequality by 9.3 standard deviations using the light of quasars. There is no second kind of matter that you are made of. No special exemption granted to things that have become complicated enough to ask questions about themselves. Whatever it is that the experiments revealed about the nature of physical reality, they revealed it about the nature of the physical reality you are. The non-separability is not a fact about distant photons. It is a fact about the kind of thing that exists. And you are that kind of thing. So the feeling you have right now, the bedrock certainty that you are a single, bounded, definite object, occupying one location, carrying your own private set of real properties, sealed off from the rest of the world by the obvious fact of your own separateness, is the human scale version of precisely the picture that nature has ruled out at its foundation. I am not telling you that you are not real. I want to be careful here, because the danger at this point is to slide into mysticism, into some warm cosmic oneness. And that is not what the physics says, and it is not what I am saying. The physics is colder and more precise than that. It says that the property of being a separate thing with definite independent characteristics, the property you assume is the most obvious fact about yourself, is not a fundamental feature of reality. It is an appearance that emerges at large scales from a substrate that does not have it. You are a stable, persistent pattern in a fabric whose threads do not respect the boundary you feel so certain marks where you end and the world begins. And nobody, not in any of the rooms, not in Copenhagen or many worlds or Pilot Wave or anywhere else, can tell you what that boundary actually is, or whether, at the level where reality is doing its real work, it is there at all. This is what Einstein turned away from. Go back to the beginning, to the headline, to the grandfather. The New York Times called him a sort of grandfather of quantum mechanics in 1935, and the word was kinder and more exact than they knew. Because what a grandfather does, in the end, is bring something into the world and then watch it become something he does not recognize and cannot control and does not want. Einstein helped father the theory. He gave it one of its founding ideas and won his Nobel Prize for it. And then he watched it grow into a description of reality that violated everything he believed reality had to be. And he disowned it, and he called its strangest feature spooky, and he spent the rest of his life insisting the child was sick and would have to be cured. He was the father who could not accept what he had made, and the child grew up anyway, without his blessing, and turned out to be right. The word he chose, spooky, has lasted almost 90 years, and it has lasted because it is perfect. And it is perfect for a reason Einstein did not intend. He meant it as ridicule. A spook is something that does not exist. A superstition, a ghost story you tell to frighten people who do not know better. And by calling the action at a distance spooky, he was saying it belonged in the same bin as haunted houses and table rapping, the kind of thing no serious adult believes in. But a spook is also something that is there and should not be, a presence that violates the rules of the solid world, an influence with no body, reaching where nothing should be able to reach. And that, it turns out, is exactly what the experiments found. Not the absence of the spooky thing. Its confirmed, measured, Nobel-certified presence. Einstein reached for the most dismissive word he could find, a word meant to consign the idea to the realm of things that are not real, and the universe took the word and made it literally true. The spooky action is real. The ghost is in the machine. It has been measured to a precision that excludes chance to less than 7 parts in 10 to the 21st. And it was confirmed using light older than the earth, and the man who named it died certain it was a fairy tale. I have spent an unreasonable amount of time with this story, more than is probably healthy, and I will tell you the part that I still cannot think my way to the bottom of. It is not the distances. It is not the 9.3 standard deviations, or the quasar light, or the kilometer of separation between the diamonds. It is the chair, the empty chair that all of this kept arriving at. Einstein asked the deepest question anyone has ever asked about whether the world is made of separate real things, and he asked it in 1935. And then the universe took 67 years to answer, and it spent the first 9 of those years just waiting for him to die. He could not have heard the answer. The argument that made the question answerable did not exist yet. He had no way of knowing, no possible way, and so he did the only thing a person in that position can do. He decided. He looked at the fork in his own argument, the one branch leading to an incomplete theory and the other leading to a non-separable world, and with no evidence either way, with nothing but his own conviction about what reality must be like, he chose the branch that let him keep the world he understood. And he was wrong, not because he reasoned badly. He reasoned better than anyone. He was wrong because reality is under no obligation to be the thing that a great mind needs it to be. That is the part that should follow you out of this, not the physics, the position you are in. Because you are in exactly the same position he was right now about the things you are most certain of. You are walking around inside a set of assumptions about what is real and what is separate and what is solid and what is there when you are not looking, and you did not arrive at those assumptions by evidence any more than Einstein arrived at his. You absorbed them. You are swimming in them the way he swam in his, so deep that you cannot see them as assumptions at all, only as the obvious shape of the world. And the one time we managed to drag one of those assumptions out into the open and put it to a real test, the most reasonable assumption anyone has ever made, held by the most reasonable man who ever lived, the answer that came back was no. The reasonable thing does not work. Bell said it, hoping it would not be true, and it was true. The experiments are finished, the loopholes are closed, all of them that can be closed, back to within a sliver of the beginning of time. The number is 9.3, and it is not going to move. What remains open is not whether the world is locally real, because it is not, but the only thing that was ever really at stake, which is what you do with a fact you cannot live inside. Einstein could not live inside it, so he denied it, elegantly to the end. The interpretations cannot live inside it, so they pay any price to look away from the flaw. And you are going to walk away from this, and the room behind you is going to feel solid, and the chair is going to feel like it is definitely there, whether you look at it or not. And you are going to go on being a single separate person in a single definite place, because that is the only way a human being can function, and none of it is the way the world actually is underneath. He called it spooky to make it go away. It did not go away. It was confirmed and honored and built into the machines that are being switched on right now. And it says that the world is not made of separate things, and that means you are not one either, not at the level where the universe keeps its real accounts. Einstein spent his life defending a wall between here and there, between this thing and that thing, between himself and everything else. The wall is not there. It was never there. He died with his back to the door he had drawn himself, still working the equations, still certain the wall would hold. The answer came 9 years later. It is still coming, and the chair is still empty.